Today I will talk on fractal multiquadratic approximant and their applications and some box dimension results. So here uh, mainly, so this audience is very much different, right? Because when it comes to the fractal functions, so when I started my PhD work around 97, then we had only the fractal functions were there in the linear setting, that is linear affine fractal functions. Then we developed different type of fractal functions. But in this context, so here we'll talk about little bit on fractal functions because several people may not be familiar with that one. Then why I construct fractal multiquadratic functions, I will give that motivation why for going for this fractal multiquadratic, or in particularly we developed what is called a fractal radial basis function. And then there are some box dimension result and some applications are there. So this is the basics of fractal interpolation function. Suppose we have some data is there. Okay. So in order to construct a fractal function, we need a contractive map in the x direction, and we need another contraction in the which will take care of our y coordinate, that will be taken by this map vi. So that this will satisfy this condition. And here we need this vi has to be contraction with respect to y, and in x in the first coordinate it can be liquid. So we will get our wi xy. So this is the elementary IFS setting. We need this wi. So this is the IFS we need. So if you take this IFS, then you can construct actually, in particularly if you take vi xy equal to six plus mix, and in particularly this is cix plus bi. If you take this linear map, here you can write this IFS in this setting, and you can compute the values of ai, ci, bi, and ei. So here this fractal nature of this fractal function depends on the scaling factor s. So one can get actually, one can define the what is your state value Hutchinson map, and you'll get this attractor of this w, so which is g. So g is nothing but we'll get a function whose graph is g. Okay, this f is called fractal interpolation function. So in particular, if you go for a function space g like this, f is I to r, where f is continuous and satisfying these two end condition, we'll get define a RV operator in this manner. And this fixed point of this RV operator is the fractal function, because this graph of f star is equivalent to this attractor g. So therefore, we got the fractal function. And these fractal functions can be constructed iteratively. So therefore, we'll get this one. So if this is the data point, so we'll get this fractal function after certain iteration. So this graph, this is self-affine in the nature. So in order to construct the differentiable fractal FIX, so Bransley Harrington, they give a formalism, but they are difficult to construct the fractal functions with different type of boundary conditions. So we gave that idea. So here what happened actually in the latter part of my talk, we need the fractal functions whose derivative is irregular. So that's why I just gave this construction. So one can construct the fractal functions. So this is a smooth fractal function. So this is twice differentiable fractal function. But if you see the second derivative, it is very irregular. So this is a spline fractal function. So similarly, you can get this type of spline fractal functions, which are very useful for the geometric modeling problems. So when you take this scaling to be 0, we'll get the classical splines. So therefore, these fractal functions, they generalize the classical spline. So now we'll move to fractal multiquadratic function. So when we saw these fractal functions, we developed different type of fractal functions. Then this fractal function, when you go for the different type of domains, so we found actually fractal dimensions. So it is not possible to construct fractal surfaces in various domain actually. So if you see the fractal surfaces, initially they constructed over the triangle, because it is easy to map a side of the triangle to another side of the smaller triangle, then you can do this one fractal surfaces. So similarly, fractal surfaces was developed over the rectangular region. Okay, but when you have data in arbitrary settings, okay, suppose I have some data like this. Okay, so now this question is whether I can construct a fractal surfaces over this type of arbitrary data. So if you have something called scattered data, which is scattered interpolation, will get such type of situation. So there you need something called a radial basis function. So because this was given by multiquadratic function by Hardy, this is not the same Hardy, it is LR Hardy. So in order to approximate some topography actually. So he used a different technique. So what he did actually, so he took a function actually. If you want to approximate any function, so if you want to approximate any function, so summation some j equal to 0 to n. So some lambda I. So phi of x minus xi, if I am approximating on R actually, so I can write in this manner. Okay, in the higher dimension, similar things will work. Okay, if you go for Rn, here you have to replace this one by norm of that. And this type of function, it is very popular to solve in PD actually. And recently actually, so this lambda I, when you are approximating this lambda I, okay, so if you in the machine learning problem, okay, so they want to optimize lambda I. Okay, so my aim was whether I can construct fractal functions which will be useful in various domains, as well as it will be in the machine learning or a differential equation in the different things. So I want try to connect these fractals into various domains. So that was my aim. So that's why I thought there is no radial basis function in the fractal. So my aim is to whether I can construct some fractal functions in arbitrary domain. So there are different type of fractal multiquadratic function. Out of 32 function actually, this multiquadratic is very popular. And this is used for this scatter data interpolation as well as solution of in the application side in RBF one can find C surface temperature modeling, then delay differential equation in fluid dynamics, different type of numerical mixing problem. So these are different applications are there. So this radial basis function, what is our objective, because this radial basis function that is used to approximate any function, and fractal interpolation that is also used to interpolation as well as approximation. So they are very much common in the nature. So that's why we thought whether we can combine these two different areas and develop some new things. So that's why we go for this fractal multiquadratic function or fractal radial basis function, because in radial basis function, in particular case, you will find a fractal multiquadratic function. So here in different physical phenomena is there, where the derivative of this function will be a fractal function. So therefore, it is if we are finding, if we are modeling certain problems, so where the derivative is irregular, okay, so then this fractal RBF may be useful. So here I am going for this fractal multiquadratic function. So this is the popular fractal multiquadratic function, phi r equal to square root of r square plus c square. So this phi can be taken in this manner. So here r belongs to 0 to infinity, which will be used to deal this function which is defined over x1 to xn. Suppose you have some data is given over x1 to xn. So here we have to construct a different domain. So you construct the delta from this data. Okay, so if my sigma is, so it is depends on what is my this omega. Suppose here I have taken 2, 5, 10 or 18, whatever may be. Suppose in one dimension. So then here I have to find what is my k actually. So this k will be here maximum of 18 minus 2 in one dimension setting, it will be 16. So I have to construct a fractal radial basis function because it is radial basis. So it says that it has to be symmetric. So I have to construct a fractal radial basis function from 0 to 16 here. And the left hand side also I have to keep minus 16. So I have to construct a fractal functions which will be self-similar here. So original problem is given somewhere. I have to construct a fractal function in a different domain, then I have to match them together. So here, so we construct this k actually. So this is the traditional setting x to primum of x minus x. You take the maximum value. In this case, one can get 16 here. Okay, so therefore one has to develop this fractal function over minus k to k. So therefore you have to split this interval. So you have to take various rij. So here, so you have chosen these are the partition of this interval. So one has to define what is the UIR. So earlier we were in a different domain. So now I have restricted my domain to minus k to k. Here I have to construct the fractal. Then I have to generalize this one to this domain. So similarly, here you have to take VIRT equal to alpha IT plus QIR. So this alpha, this is called scaling parameter. Here we are going to generalize this multiquadratic function. So here I can take QIR. This is the fractal perturbation method, which we worked a long back actually. So this is phi of EYR minus alpha I. So this is the base function. It is for multi-quadratic. So we have taken this will satisfy this end condition. So here we have not imposed any differentiability condition. This functions, multi-quadratic function may be nowhere differentiable. So therefore one can think of defining RB operator. Okay, so it has to be defined very carefully so that this function has to be symmetric over a larger domain. It is around 0 because when I go for the higher dimension, I have to preserve the similar nature. So therefore, one has to define what is the RB operator here. So this has to be defined in both left hand side and right hand side in suitable way. So this is we have taken different subintervals in both left and right side. And then we have to define this space G, and if it is endowed with the supremum norm, then we can get one can prove that this T is contraction, then you will get the fixed point here. So when you take alpha equal to 0, it will match with the classical multi-quadratic function. This paper is simply accepted in the sign on. So here I am giving one example. So suppose our grid is function is given over 0, 1 by 6, 1. So here in this case is straightforward. So we have to see all these points. The difference between 0 and 1 by 6, it is 1 by 6 is already there. Between 1 and 1 by 6, we need that point 5 by 6. So we have to extend this domain in this manner because it is applicable in certain PD or ordinary differential equation. They need this type of setting because all these values are required. So we have to choose the multi-quadratic function in this manner so that it will satisfy the end condition. Phi of r equal to, we have taken some particular value of c here. We mentioned c equal to 2, 120. So we take different values of alpha. So we construct different type of fractal function which is symmetric about the origin. So here if you take this, so here you can see the fractal function. So here we have taken c equal to 2. It is symmetric about the origin. Similarly, here we have another type of fractal function. Here c is 20. Okay, so if you go for the higher values of C, this graph may be a little bit smooth. Similarly, you can go for the negative scaling, you can get different type of multi-quadratic function. So if you want these, instead of these functions are very irregular, so if you want smooth function, so one can choose the alpha to be less than equal to, suppose it has to be p times differentiable, then alpha has to be chosen ai to the power p, and this base function has to satisfy this condition, so that we will get this self-referential equation. So that means this type of multi-quadratic function will be smooth in the nature. It may be differentiable. So here this function is convex in nature. Phi r equal to square root of r square plus c square. So this is the convex. So whether you can construct the, if you do the fractal perturbation, okay, so it may be irregular. So the question is whether you can restrict the alpha and the base function so that this function is going to be convex. So you put some appropriate restrictions here. So this work already we developed how to develop the self-preserving fractal function to use that idea and get this function to be convex. So I'll skip the proof due to time constraint. So then we'll go for this higher dimension. So here we construct the fractal, this fractal radial basis function in the higher dimension. So here suppose I have this domain xi a is there. It is not in now R. Suppose you go for this arbitrary setting, okay, Rn or R. So there you can take these points are there. So one has to compute what is the k. So what is the maximum value between the supremum of x minus xa. So therefore you have to find this value. So based on this k actually, so now you have to construct the fractal radial basis function over 0 to k. So first we have to construct small phi r equal to square root of r square plus c square. So you take a partition in the right hand side, then you replicate the partition to the left hand side, and then so you construct this map vi on the similar way, but it has to be in the higher dimension. So we'll get this base function, then we'll get the what is the fractal radial basis function. So similarly, one can define what is the RB operator here, which is has to be contractive in nature. You take a function space here satisfying these end conditions. So you can think of RB operator, it will give a fixed point because this is the contractive in nature. So therefore, we'll get a fractal function, fractal perturbation of the small phi. Okay, but I have to define the fractal function over an arbitrary domain. So this is over Ra. Okay, so therefore here this is the this radial basis function. It is Rs to R. So this has to be defined in this manner. Phi alpha x equal to the small phi alpha is already defined. Okay, so this function is a function in one dimension. So therefore you have to write phi alpha norm of x. So this is termed as fractal radial basis function, where phi alpha is a fractal function corresponding to previous IFS. So here we have given the example. For simplicity, we have given 0, 1 to 0, 1. So here you can find the maximum value of k will be root 2. So therefore, I can construct the fractal radial basis function. That means it will be in the radial direction up to root 2, it will be self-similar. So consider the phi r equal to square root of c square plus r. So here I think we have taken this inverse multiquadratic function. So you take a partition here, and then you choose the base function h9, which is the h9 is the generalized Hermitian property, which is differentiable 2 times. So therefore, we define different type of fractal radial basis function. Since we have restricted the function up to a square, so that's why you are finding this step is missing. Otherwise, if you see in the radial direction, so all these functions, okay, so they are very similar along the radial direction. So when you approximate a function in the higher dimension, we have to take such type of basis, then we have to shift it, and then you have to find the appropriate values of lambda I, so that you can approximate any type of surface. So here, now this question is when we are constructing some fractal approximant, because this fractal approximant, it is nothing but this is the summation of some lambda I, and this type of phi will be there. So our function is, so this is the fractal radial basis function. So we are approximating any function actually. So that we have to find what is the fractal dimension of the functions which are linear combination of such type of functions. So this I think you can see here when this value of alpha is very high, so it is very irregular in the nature. Otherwise, if it is small, it will be smooth actually when these values are little bit small. Okay, in the approximation we did the other way. So we got the different type of phi alpha, and then we have to, this phi jx nothing but a translation of phi alpha x minus x. So this meaning of phi j alpha x is phi alpha x minus x. You have to shift the function by x. So here this is the standard definition. Now our aim is how to get the some dimension result for this function s alpha, which is the union of this linear combination of all those multiquadratic functions. So we'll prove this result for x equal to 2, and because this proof is very similar if you take x bigger than 2. So here I is 0 to k, delta equal to 0 to 1 by 2k. So MB the least number of positive integers less than equal to 1 by k delta. So I think so this result is well known. Thanks to Falconer, he have given this estimate. So we'll use this estimate for this small phi alpha, but we have to shift the result to capital phi alpha, because capital phi alpha, which is defined over a different domain, so that is defined through the small phi alpha. So here you can choose actually when you take s equal to 2. So we are moving along this radial direction, so we'll get a strip actually. Okay, so when you compute the number of cubes actually, which is lying in a strip, so here we have taken a so cubes actually in this form, it will be there in the annulus. So we have to see carefully, okay, and then you'll find what is the number of balls which are intersecting this strip. So we'll get this estimate. This C0 is coming because when you take the radial direction, you'll find what is the perimeter. That 2 pi factor will be there, so one can get this estimate. So using this above result, we'll estimate the bound for the upper bound of box dimension of graph of S alpha phi, S alpha over this. This is your sigma. So therefore, for this dimension part, so we are taking S alpha x equal to summation of j equal to 0 to n lambda j phi j alpha x. So here you have to compute the upper box dimension is less than equal to 1 plus dimension of this small phi alpha. Okay, because this dimension result for the small phi alpha is known to us, so therefore we can get this result. So here this calculation, so here you have to shift the, because this graph of this one, this is shifted by this xj, so xj 0 plus we have to shift the ball actually here. So therefore the number of balls which is required to cover this one is equivalent to the number of box which is required to cover this graph. So therefore by using the previous estimate, so one has to count the number of balls. So here some calculations are involved, so I'll skip this one due to time constraint, and here one can find actually, so this number of balls which is required to cover this graph of this fractal radial basis function, it will be less than equal to this one. And here this lambda equal to maximum of all these constant lambda 0, lambda 1 up to lambda n, which is coming as a linear combination of this. Okay, then if you apply this standard definition, you'll get this value is less than equal to 1 plus dimension of g of phi alpha. So this is a one-dimensional function. We know how to compute the dimension of this one. So similarly, the question is whether you can get the exact dimension. So it is a little bit difficult actually due to the radial nature of this function. So therefore, we took actually r of xij in this manner, xij equal to supremum over this x belongs to this domain x minus norm of x minus xj. So here some values may be same actually. So when you vary this value, so therefore we have to arrange these elements in the R in ascending order. Okay. So that this zeta 0 less than zeta 1, zeta n 0. So this n 0 will be less than equal to n due to some values may be repeated here. And then you have to define what is happening. So in this, we assume this domain to be a convex and compact subset of R2, and we introduce the annulus here. And in particularly theta n 0 equal to, here you can take zeta n 0 minus zeta n 0 minus 1. So this n 0 is important because this plays important role to calculate this lower box dimension. So here we put some conditions so that this upper box dimension and lower box dimension will be same. Okay. Suppose phi alpha and lambda j in 20 satisfy the following three conditions. So this dimension of this 0 to k, so this function has to be small phi alpha, this has to be c. And there exists a unique j0 belongs to n0 such that this coefficient must be non-zero, because we get this coefficient when solve the system of equations. So there is no guarantee that this will be a non-zero. Okay, so therefore in that case, and you assume that zeta j less than equal to zeta j0 for every value of j, and we assume this condition a little bit strict actually, so we don't know whether there is any other condition. So in that case, we'll find this lower box dimension is going to be the same, then you can get the what is the exact fractal dimension, box dimension of this type of fractal radial vector. So I'll skip this part due to applications are there. So one can compute this result. And now I will show this application of this fractal multiquadratic functions in the solution of the differential equation. So when you have some differential equation like this, suppose the solution y equal to, so this is n times differentiable, but you take nth differentiable of this function, maybe nowhere differentiable function, like Weierstrass function or anything. So in that case, whether you can get the how to get the solution of such type of differential equation. So here we have used the collocation method. So you take the partition of this domain, then you add the collocation point here, and then you define the fractal perturbation of the given function by using a different radial basis function. Here it is the exponential radial basis function we have used. And then we can get the system of equation where you have to compute all these values of lambda j. And this part is coming from the collocation point. So therefore, use the initial conditions and one can find the number of equations and number of unknowns are same. And then we'll solve this initial value problem. In particularly, we have given y dash plus y equal to eta x. For eta x is a fractal function. That means it is very regular in the nature. So this eta x we have plotted here somewhere. So this is the eta x. So you want a differential equation whose right hand side is very irregular in the nature. So this analytical solution is known to us e to the power minus x plus f beta x. So here by using this initial condition, whether you can use the fractal RBF method to solve this type of differential equation. Here we have taken a partition, then we have added a collocation method, then we approximate the solution in this manner. Then we have to solve this value j equal to 1 to 4 lambda. We have to compute the 6 parameters are there. So we have to solve a system of equations. So this is the fractal perturbation which we have explained. And then we solve these values of lambda j. And we have given some observation depending on this values of theta or b or alpha, you can get the different type of solution. So for this original solution here, so this is the exact solution of this differential equation. So in the classical method, one can get the solution like here. But when you apply the fractal solution, so you can get the for different values of parameters, one can get the better solution. We have not used any optimization technique like genetic algorithm or other things where you can get the better approximation to this analytical solution. So similarly, there is this is the application to the differential equation. Here, this is the approximation by the fractal MQ functions. So here one can take this as x equal to in this manner. Here you have to add two more. So this is the multiquadratic function, and here you have xi0 and xi1, two more parameters are there. So you want to approximate this any function actually satisfying this condition. F is the function which is known to us, or you know the sampling values here. Then we have to approximate this function through this fractal radial basis function. It was given by the Bitson and Powell. So here we modify this one. So instead of taking this function, we can go for the fractal perturbation of this one. So we propose this one, you go for the fractal perturbation of this function, and then you take this approximation, then you can get this. This error estimate is going to be less than equal to m times h, where h is the maximum of your gate distance. So here we have given some application. If this is the function which we are going to approximate by the fractal radial basis function. So here we have used the different type, because we have the plenty of parameters are there. Alpha is there, B is there, C is there. So different type of parameters are there. So one can get the different type of fractal function. Here we have taken the zoom version of the previous picture. In the classical case, we'll get this one. So which is very bad, this red one. And this original one is here, pink one. So therefore, if you apply the fractal technique, so here we have not used any optimization technique to get the appropriate values of parameter associated with the radial basis function. So similarly, this is called fractal quasi-interpolation, because there is a demerit when you apply this fractal RBF. So here one has to compute the system. So here there is no guarantee that this is well conditioned. So therefore, in order to avoid this lambda I, so there is another way. So one can define what is called quasi-interpolation. So one can define what is this LC. So we define this LC alpha fx in this manner. So this is the quasi-interpolation. We take the fractal perturbation of this radial basis function to define this quasi-interpolant, and then we approximate any function which is either differentiable or non-differentiable. So here we have given how to approximate these values based on that same idea. So you take the fractal perturbation of this psi j, and then you fractal perturbation of phi j, and you construct psi j based on this one. Similarly, beta 0 alpha, beta n alpha, all these functions have to be constructed, and then you'll get this is the derivative of this function. Now the question is whether you can construct a function whose derivative is similar to this one. So here this original graph is given, and different approximation in the classical case as well as a fractal have been given. It is found that in the fractal case we have very less error, and here the derivative will be irregular, but we have not optimized the rate. So similarly, we have given the function which is twice differentiable. Sign is there. So here this function is twice differentiable. So we have to similarly we have to define this operator LC alpha. So for different values of k equal to 1 to 2, we have taken two different cases here depending on which scaling factor, whether you are taking this one or that. And here we plot all these functions. You give the original function, and then you take the fractal perturbation of this one approximation. So this fractal quasi-interpolant they have computed here. So the second derivative of this function is very irregular. So we are constructing the fractal function whose derivative is very irregular. So we are applying this quasi-interpolation to approximate that function. Here you can see the original function is there, is the blue one, and here you have two quasi-interpolants are there. And in particular, if you take alpha equal to 0, you will find the classical one. So we have given the here the zoom version of this given. When alpha equal to 0, you can see the blue line. In the classical case, you will get more error, but if you take the fractal one, this error is very less. So here this, so if you see the derivative, second derivative of this interpolant, it is also not optimized. So that's why you're finding it is varying from the original function. So here you give this convergence result. Okay, so if you are getting this quasi-interpolant LC alpha f minus f, whether it is going to 0 or the partition is going to 0. So here we have given some estimate. So under certain assumption, you can get the order of a square convergence. So similarly, if you take this, in particularly, if the scaling factor is of order h to the power 4, one can get the error estimation to the order of a square. So then there is a self-preserving result. So if the original function is convex or concave, even if linear, so then you can find this function LC alpha f that is also going to be convex or concave or linear. So here f is a convex, so Here you can write actually this LC alpha. This is the fractal operator. You have to see the second derivative, whether it is going to be, if it is convex, original function is convex, this derivative, second derivative has to be positive. So one can write this expression, and then you can verify this each term here actually they are going to be positive. So therefore the second derivative is positive. Therefore f is this function is going to be convex. Similarly, if you assume this original function is concave, so here you will find these all these terms which are in the brackets, they are going to be less than equal to 0. So we'll find this is concave, and similarly if it is linear, you'll find these expressions are going to be 0, and we'll get this result. So the next example, again we have one for another concave function. Here, both concave and convex functions are there. So this is the original function, x minus 0.5 whole square, which is convex in nature. So we use the fractal multiquadric quasi-interpolant here, and we found a function which is very close to the original function. Similarly, here it is concave, so we got this by fractal perturbation method. One can approximate this. So similarly, there is another quasi-interpolation operator LD. This in classical approximation theory, there are three types of this type of quasi-interpolation operators are there. So we generalize two operators here. One is LC alpha. In LC alpha, we need the derivative value at the both endpoints. But when you go for LD alpha, we don't need the derivative value. So in case there is the derivative values of this, our approximating functions are not available, then one can apply through this operator, quasi operator LD alpha. So here this function is defined over x0 to xn. So this is the suppose values are available at these points, interpolation points. So now one can define a new fractal quasi-interpolation operator in this manner. So here these operators are again defined through this perturbation of phi. So we took that one. In particularly, when you put alpha equal to 0, it will match with the classical one. So in this convergence result, we assume the scaling factor alpha I has to be ai square, because we need the function has to be twice differentiable. So therefore, we put this assumption here. Suppose f is twice differentiable, so we can put the condition alpha I has to be less than ai square. So this is the maximum distance. So therefore, this is the error estimate with the fractal here f is missing. So f minus LD alpha f. So this is less than equal to c. In particularly, if this c can be taken as order of s, you will find this approximant is going to be this convergence will be order of s square. So again, one has to split that operator quasi-interpolant, and one can write in this manner, and then we'll get this result. So here I'll give the application. So if you want to approximate this function, which is twice differentiable, so whether you can get the better approximant or not. So here we have shown actually when you take alpha equal to 0, so this is the blue line, and yeah, this green line will give the better approximation. Here alpha equal to 0.009, it gives the better result, because when you compute the error actually you zoom the if you take the error part, here one can observe this. In the fractal case, alpha equal to 0.009, this error is very less. Although in the classical case, this is 0, 0. You can see the blue curve, it will come from the classical error is more. In the fractal case, this error is, it is going to be less. So similarly, we have approximate this one for irregular function, not necessarily only smooth functions whose derivative is irregular. Even if we have functions which are very irregular in the nature, one can construct the fractal multiquadratic function. And this operator will give you very good approximation. So here you take this original function, which you can see this is the blue one. And in classical case, if you take this one, this is the red one, which is very bad approximation to irregular curve. So here we apply the fractal multiquadratic interpolant, quasi-interpolant, and we got the different type of approximation depending on the different values of alpha. We found that they are better approximation to the existing approximation. So these are the few references. Thank you for your kindness.